Okay, let's continue on with some more background information that you need for the assignment. So I'll be talking about the IJVM instruction set and the information you need to implement it. So let's take a step back and talk about virtual machines. So most of you are probably familiar with virtual machines, and you've probably seen it in the context of something like you see here on the screen, running something like VirtualBox, where you can run Linux inside a Windows machine or Windows inside Windows and so on. But a virtual machine is kind of broader than that. So it's not always only used for running a certain operating system inside another operating system. So basically virtual machines run an emulated or virtual version of a certain computer system. And this is based on an instruction set architecture. So for example, if you go back to the example here with VirtualBox, you usually run your own instruction set inside your, you run the instruction set that your machine is running. So if you run x86-64, you would usually run x86-64 guest here, and it uses hardware features such as Intel VT to actually achieve this with a low overhead. But for other cases, you might need to emulate the whole instruction set. So, for example, if you run an Android emulator with the ARM target on your laptop, you will probably need to emulate the instruction set, the ARM instruction set, or AArch64. So we have a bunch of examples here of instruction sets. So normal x86 or x86-64 that all of you are probably running that one. Then there's the RISC-V, which is kind of an open source instruction set architecture. The Java virtual machine has its own instruction set, and your phone probably runs AArch64 or ARM64. So basically this is the set of instructions that your computer runs. You should have learned about this a bit more during the computer architecture course. So I'm not going to cover the intricate details of all these instruction sets at the moment. But usually the layout of a virtual machine is something like this. So you get as input bytecode here at the top level. Then your virtual machine, which is here, runs, interprets this bytecode and translates it into the real hardware instructions that are run on your hardware. So suppose you have Java bytecode, the Java virtual machine here would interpret the Java bytecode into x86-64 instructions if you run it on your laptop, for example. And then of course you have the operating system, which is kind of besides here. So usually the virtual machine is an application inside your operating system, or it's a part of the operating system, such as KVM on Linux. There's a few different architectures here, so that's why they're next to each other. So the operating system is mainly concerned with I/O with the hardware, while the virtual machine here runs the direct instructions that you want to execute. So internally, these virtual machines have three main steps basically when interpreting bytecode. So the first, you get as input a bytecode file. Then the VM starts its main loop, which first of all it starts fetching an instruction. So it starts trying to read an instruction. Then it needs to decode. So as you already know, like you have different instruction set architectures, and the way that instructions are represented in these instruction sets differ wildly. So some instruction sets have fixed length instructions, but other ones have variable length instructions. So the decode step kind of takes, whatever, it decodes the instruction that you're reading and kind of tries to understand what it needs to do. And then the last translation step takes that instruction and translates it to the architecture that you're on. So typically something like this, what it would do is like it fetches an instruction from a lookup. Well, it fetches an instruction, then looks it up in a lookup table to say, okay, this certain opcode corresponds to something like that, so handle this instruction. Then the decode step would probably be this handler here, tries to decode the instruction, and then finally you translate it and execute whatever that instruction is supposed to do on your hardware. So onto the IJVM. I already mentioned that it's the integer subset of the Java virtual machine. And it's a quite small subset. It only has 24 instructions, so it's quite manageable. You can have a nice overview of it. Well, you can fit it inside your like normal memory. So this instruction set was created by Andy Tannenbaum for educational purposes for his Structured Computer Organization book. So I don't think you use this book anymore for the computer architecture course, but it used to be the it used to be the course book for the predecessor to that course. One nice thing about the IJVM or the JVM for that matter is that it's a stack-based machine. So the instructions are pretty simple. I'll come back to this a bit later, but basically you have stack machines and register machines. So something like x86 is a register-based machine where every instruction has different variants depending on which register you want to move from. Well, a stack machine usually just reads the arguments from the stack. So first of all, we have to go back to the stack. So what is a stack? Well, you've probably already seen this. So I think you had an assignment on this during the C++ course. But just to refresh your memory about this, it's a last in, first out data structure. Well, as the name already suggests, it works like a stack of papers. So basically it has 4 main operations. Pop, which removes the top of the stack and returns the element. Top or peek, where you just have a look at the top thing and put it back. Then push is to put a new paper on top of the pile. And size, which returns, well, how many papers you have on your pile. And the classical simple way to implement this is using an array and a pointer, and this pointer we usually called a stack pointer. So let me give you an example of a simple stack machine. So for example, a reverse Polish notation calculator is example of a stack-based machine with a really simple instruction set. So I don't know if any of you have seen these calculators at some point. They're pretty old, but you can still find them. So basically these things work with a stack. So you add a number like 1, 2 plus, and it will return 3. Here you do 1, 1, 1 plus plus, which means push 1, 1, 1 to the stack and then do plus. So this will also return 3, and so on. So basically the instruction set consists of 4 different opcodes, or technically speaking like 13, but okay, so basically you have 3 operators, so plus, minus, and multiplication, and then you have 0 to 9, like the digits that you can push on the stack as arguments. So this is a super simplified instruction set architecture for a reverse Polish notation calculator that can only handle single digit numbers, but it's just I've kept it simple so that I can show the whole code for the implementation of this in one of the next slides. So to make it more concrete, let's have a little example on how these things, how an RPN calculator works. So basically you have your stack with your stack pointer here, and then above here you see the input that we want to read and evaluate. So the first input character is a 1. So what you do is you take this 1, push it onto the stack, and increment the stack pointer so it points to this element. Then you read the next character, which is a 2. Well, you do the same thing. The next character you read is a plus, which is an operation. So if we go back here, you can see, okay, now you have the stack consists of the number 2 and 1. And basically what the plus operator does is pops these 2 things from the stack, adds them together, and pushes the result back, which is 3. So you can see that the previous entry here has been cleared, or well, it's not there anymore. Then we read the next input byte 2, for example, and which pushes 2 to the stack. We push 1 to the stack, and then we do a minus, which pops both like the top 2 values from the stack and subtracts them from each other. So it will do 2 minus 1, if I remember correctly. And it pushes the result 1 on top of the stack. And then finally, we read another plus operator, which will simply pop these 2 things from the stack and push the result, which is 4. So fairly simple. Here you can see all the different steps. So you can look at this back a bit later, I guess, but it's just to give you an example of how an RPN calculator works. So this thing, let's discuss how to actually implement a simple calculator that works in this way. So first of all, we want to implement a stack because, as I already said, it's a stack-based, like a stack machine. So here's an implementation of a stack. So we implement 3 of the different kind of methods on a stack, pop, top, and push. But before that, we first allocate an array of integers here called stack, and then we have a stack pointer that points to a certain index into this array. So the pop operation, first there's an assert here. You can ignore that for now. It's just to sanity check that the stack pointer is actually valid, that we're not trying to return something that doesn't exist. And what it does, it returns the value at index sp, so the stack pointer index in your stack, and then decrements the stack pointer. Top does basically the same thing, but it doesn't decrement the stack pointer. And push does the opposite thing. Well, it increments your stack pointer first and then writes a certain value to that new location in your stack. Fairly simple. That's how you implement a stack in C. So on to the main calculator part. So if you can remember, like from a few slides ago, I was talking about the 3 different stages of virtual machines. So you have fetch, decode, and translate or execute stage. So let's try to map this to this RPN example. And of course, you can implement this in a few different ways. So here I've been trying to keeping it super concise. It fits in one slide. So first of all, well, we enter here, we set the stack pointer to a negative value, well, kind of undefined stack pointer. And then we start a loop that just keeps looping. So first of all, we have our fetch stage. And that's here, it simply calls the C standard library function getC. So it reads 1 character from the standard input. So if you type in 1, it will read the character 1 and so on. So, okay, that's the fetch part. That's really simple here. Then the decode part basically starts at line 42 here. And it's a huge switch statement that just checks, okay, for the opcode that I just fetched, what should I start? Yeah, what should I do? So if it's plus, it will start operating. So this is basically here when it matches is the decode stage, and then when it executes this stuff, that's the translate or execution stage. So typically you would have a function call here because it becomes quite messy if you have a lot of opcodes. But yeah, since I wanted to show this in one slide, I simply inlined all the kind of execution and translation stages here. So if you have a plus, well, it will pop to things from the stack and push the result, like the sum, back. Minus thing, well, very similar. Multiplication, yeah, same thing goes there. Then we have some other cases here. So if you read end of file, which means that there's no more input, then we just print the result, the top of the stack as a result, and exit. We also, if someone enters a new line, we also print whatever is on the top of the stack. And in any other case, we just push that value to the stack, and it does here, like, so it reads the character, right, and then does minus the character 0, which means that the ASCII character 0 will correspond to the value 0, ASCII character 1 will correspond to the integer 1, and so on. So it's just converts between ASCII and integers. So, okay, you have now seen how to implement a simple stack machine or RPN calculator. So let's tie this back into the IJVM that you have to implement. So the IJVM is similar in nature to the RPN calculator that I just discussed. So it has some operations that are fairly similar. So by push corresponds exactly to the constant things that we just pushed to the stack. So if you enter one of the digits, that's pretty similar to this instruction here. So you have stack operations. So you also have a pop, like similar that we already saw, I add, which adds 2 elements from the stack, and so on. But of course, we can do a bit more with this than with just normal reverse Polish notation calculators. So this is actually a subset of the Java virtual machine. So you can run some real programs on this. So of course, it supports branching operations such as goto and if equal, well, a few different branching instructions so that you actually can have some control flow in your program. So you can say, okay, if something happens, jump to this location in your program and so on. Then the IJVM also supports some memory operations, so iLoad and iStore, which basically handle, it reads from memory. That's the concise way to summarize these things. Then you have some IO instructions, so the in and out instruction, where you can print, well, they pop one value from the stack and print that to the standard output or read it from the standard input. Yeah, simple enough. And then there's some more advanced stuff like method invocation. So you can actually create methods or reusable sub-procedures, and you can invoke them. So you can do some nice stuff like recursion using this instruction set. And then there's also some debugging operations like halt and error to, well, halt the machine or print an error message. So in total, there's 24 instructions, instruction operations. The complete list of all these instructions is available in the manual. So a note about decoding the instruction. So the IJVM is not a fixed length instruction set, so it has a few different kinds of instructions. So mainly like you have 3 different ways that instruction is represented. So you have the 1 byte like no argument opcodes, and that's something like iAdd and iSub, because these things, they pop 2 elements from the stack and do some magic with that. Then you have instructions that have kind of a byte argument format. So you have the instruction start with a certain opcode, and then the actual instruction is followed by another byte, like an argument. So an example of this is the bypush instruction, which is similar to what we already looked at in the RPN calculator. But here you kind of, whatever value you push to the stack is not in the opcode itself, but the byte following the opcode. And then you have the third kind, where you have an opcode followed by either like a 2-byte short or 2 separate bytes. So an example of this is the go-to instruction, which jumps to a certain offset. So let's have a look at this. So basically you will get a binary file that has these kind of opcodes, and then you need to kind of fetch and decode these things. So in your binary file that you get as input, you would read like 2 of these, like 2 byte values like this, so 0x10 and 0x1. And then you need to know, okay, what should I do? Well, it turns out that 0x10 corresponds to the bypush instruction, so you'll have to implement a whole list matching the first opcode to whatever you want to do, and then handle them. And here the second argument is 0x1, so it will push the value 1 to your stack. The second example is a bit more involved, so here's like 3 bytes after each other, so 0x84, 0x1, and 0x5, and this corresponds to an I increase, which basically, well, to summarize what this operation does is it takes a certain memory, well, a certain local variable, to be more precise, and we'll discuss this a bit later, what local variables really are. And then it will increment it by a fixed value. So this will increment local variable number 1 with 5. So a note of warning here is that when you look at these instructions, for example, where you have a short argument, so for example the goto, so some of these instructions are signed while others are not. So the goto instruction, for example, is signed because you jump to an offset relative to where you are. But other things such as iLoad or whatever have an unsigned argument because it refers to an index. So in general, things that refer to an offset, like the goto one, use a signed value, while things that refer to an index in general use an unsigned value. So this is this is a place where a lot of you will have bugs, so keep that in mind. So basically the signedness, it's a matter of how you represent the value. So you have a fixed number of bits in a byte, and the range of numbers that you can represent with 1 byte depends on what kind of what you want to represent. So if you only need positive numbers, you usually use an unsigned value, and then like setting all bits to 0 has the value 0, and all bits to 1 has the value 255. But if you want to have use negative numbers, you represent as a signed value. So then you use something like 1's or 2's complement to represent this. This usually depends on the architecture that you're using, so keep that in mind. So if you want to read a bit more about signed and unsigned representation of numbers, have a look at the manual. We have some useful links there. Then a bit about the IJVM memory model. So basically the IJVM has a few different things that it needs to keep track of its state. So first of all, there's a program counter which keeps track of at which instruction you're currently executing. So basically what opcode or which instruction you should start fetching. And of course, this program counter is automatically incremented after each instruction is executed, and it's modified by the branching instructions such as goto. Then there's another thing called the stack pointer, which keeps track of what the top of your stack is. So as I already mentioned, the IJVM is a stack machine, so most of the operations you will do will be on a local stack. So you push values on there and do operations on it, and then you you can move it into memory. So the memory here, kind of in the IJVM, you don't have a kind of global memory. You can't refer to arbitrary memory addresses in the IJVM instruction set, but each so-called local frame, this is for later, like module 4 or something like that, module 5 even, you will start looking into local frames. But basically every method has its own frame, and this frame keeps linked to the previous frame, and each frame has a number of data for state. So for example, it has a few of like local variables. So this is the memory that we refer to here. So for example, instructions like increase operate on these local variables. So a word about IJVM programs. So the IJVM that you are going to implement executes bytecode. So basically you get a binary encoded file, which is not really human readable. So if you open it in your text editor, you will just get garbage in there. So to create programs, so if you want to test your implementation a bit more, you should create some own programs that you're executing in your IJVM. So luckily there's this thing called Java assembly. So I think this was also created by Andy Tannenbaum for his book. So for this course we have written our custom assembler, because there's also another one provided with Andy's book, but you need a graphical user interface to run it, and it's quite old and buggy. So one of the TAs from previous years wrote a custom assembler for this course. So have a look at that if you want to write some programs that you want to run in your VM. So in the end, basically, you can write programs, assemble it using our tool, and then you should be able to run it with your own implementation of the IJVM. So to give you a bit of a background on assemblers, to take away kind of the magic here, because we provide you this tool and kind of want to explain a bit what it does. So an assembler, you've probably also seen this during computer architecture. So an assembler takes a source file containing text in a human readable format and then assembles this into binary code. Besides that, it also does some other stuff. So usually an assembler translates like variable names into like indices or whatever other references, memory addresses, and labels into actual offsets. So if you have a go to certain label, an assembler usually translates it into the actual offset of number of instructions that you need to jump to the right point. So let's have a look at an example of a Java assembly program. So this is something that you in the end should be able to run on your implementation. So I think you can already, in the third week you should be able to run, well, for the third module you should be able to run this program already. So this is a simple program that pushes 10 to the stack, then pushes 1, subtracts 1, so it subtracts 1 from the value 10, then dup, which duplicates whatever is on the stack, because these branching conditions pop a thing from the stack and they're not there anymore. So if always before this thing you usually call a dup in this instruction set. But anyways, then it checks whether it's equal to 0, and if it's 0 it jumps to end. But at this point where like the value is 9, so we'll jump back, we'll continue on to the next instruction, which is bypush 0x31. which corresponds to the ASCII value of the character 1. Then it calls out, which prints this character to output, and then jumps back to this thing. And well, it loops this a few times, like until the value here is 0, and then it jumps to end and halts. So this is a very simple like a IJVM application that showcases some of the functionality that you have to implement. So how to use our assembler to actually create these programs. So suppose you have a text file like this. Basically, at some point you want to run this on your IJVM. So just download our tool, the GoJSM assembler. Here you specify the output file, so you will you create this count.ijvm binary, and as input takes this assembly file. So for example, this one. So, and then it will generate this binary. If you open your text editor, you will see some weird characters probably. So you can use something like the Unix tool xxd or hexdump to get the output in hexadecimal, so that you can actually see what's in there. So if you look at the output of xxd here, you see that okay, it starts with 1 dead fad, and that's not by coincidence. So there's this is called a so-called magic number, which signifies that this is an IJVM binary. So the first thing your IJVM implementation, when you load a binary, what it should do is check that this magic value here is correct, that it's 1 dead fad. But suppose you give it some other input file, like a, I don't know, JPEG or whatever. It should just not start executing these things, because JPEG is not going to be a valid IJVM program. Then after this 32-bit magic value here, as you can see 32-bit, or it's going to be like 4 bytes. So basically, yeah, you have this whole magic number here and match it. After that, you get to the different kind of sections in the binary itself. So each of these sections consists of, well, 3 main values. So an origin address, which you can safely ignore for now, a size, signifying how much data there is in the section. So most of the IJVM binaries that you will read in, well, I think all of them, for the additional features there, you will add some other stuff in there. But anyways, all the binaries for the test have this exact format where they start with a magic number. Then there's a section containing the constants. So it's constants that should be loaded into memory. And then the text section, which actually contains the opcodes, so the instructions that you're going to execute. So if we look at this, the generated binary, and see how it corresponds to the assembly here, well, let's start with this thing here. So basically, you have the magic number here, 1 dead fad. Okay, then you start with the next, so the first section, the constant pool. So first you have the origin, a 32-bit origin, which is this number here. You can ignore that for now. So this is used in other implementations to say where in memory to load the binary, but we don't make use of this at this point. Then there's a size, which is also 32-bit, so that's the size. Well, it turns out this program doesn't have any constants, because, well, so the size of the data block, well, data part here is 0. So if we go back to here, we can see, okay, there's no constants defined in this program at all. Okay, so then the data is size of bytes, well, read 0 here, so the size of this one is 0, so there's nothing there. Then we continue on to the next block here, which is, well, again, an origin address, which happens to be 0 here. So by the way, this is the text block containing the actual instructions. So we can skip the first 32 bits. Then there's a size. Let's see, that's this part here, which is 0x10, which means that it's 16 bytes. And indeed, if you start counting the number of bytes following this thing here, so if you add these individual bytes up, you'll see that it's 16 bytes. And okay, so basically here is the first instruction. So 0x10, 0xa. well, so if you look at this program we had, well, I think I have a better one here. Yeah, so here we can see the assembly and the binary together. So 0x10, if you remember back a few slides, was the opcode for the by push instruction. And as we can see here, indeed the program starts with a by push instruction, which pushes 0xa, which happens to be the first argument here. So far so good, right? And here you see 0x10, 0x1, which is by push 0x1, and so on. If you walk through this byte by byte, you'll see that every instruction here is actually available in the binary. So have a look at these formats and be familiar with this, because you will have to parse this during the next few days. So far we have seen stack abstract data type, we have seen stack machine, so reverse Polish notation, calculator that uses a stack to perform calculations. We've seen simple instruction decoding, so for example how to apply this to a reverse Polish notation calculator. We've seen some assembly and how assembly is translated into binaries, and well, you saw some branching in this example here, so we had to go to explain a bit how this control flow works here, so you are familiar that this kind of exists in the IJVM. So the last part I'll cover here is methods or method invocation, which is by far the trickiest part to implement. So I'll also be brief here because you probably need some more hands-on experience with the IJVM implementation itself before starting with methods. But in short, methods are reusable subroutines. So for example, you can define a subroutine called add, which takes an argument A and B. So here is some assembly where you, an example in how to define this in the JAS assembly. And I already mentioned this, you can do nice things like recursion with this, so you can implement some cool stuff. Yeah, and I mentioned it's the last thing you need to implement, like the last mandatory thing you need to implement for this course. And so if you look back at this picture that I already showed you before, so the actual example in this picture is what the memory layout looks like before and after invoking a method. So basically you have a kind of a local frame that you are in at the moment, and when you want to invoke a new method, you need to push some things to the stack. So for example, you push the parameters, but before that you need to push a so-called object reference. In the IJVM, this is not used for anything. But it's purely a Java specific thing. So since Java is object oriented, like the object reference here, refers to a certain object. But still, the IJVM keeps compatibility with the Java virtual machine, so you need to push this dummy value on the stack when you want to invoke a method. So the object reference, then you push the parameters, and then at some point you call the invoke virtual instruction. And this thing will pop the parameters from here and put them in the local variable pool. So in this new frame, the parameters will be stored as local variables, and some other magic will happen here basically. So, and of course keep in mind this is a description of how it works in hardware. So you don't, when you implement this, since you're implementing an emulator, like the only requirement is that you should take an IJVM binary and execute it. So it doesn't need to work internally. You don't need to represent your data in this way. So typically people create like a separate data structure for the local variable pool and whatever for the local frame, and store it in a different way in memory. But this is how you could, for example, implement the IJVM instruction set in actual hardware. And well, here's an example on how to return from a method, but I think it's quite self-explanatory. So you have a certain frame, you push a return value, and after returning, like the top of the stack is this return value, and you're back in the previous frame. So we had a brief introduction to the IJVM. Of course, there's a lot more to it. So I'd like to point you to the chapter from Andy's book on this. So we have uploaded this on Canvas, so you can download it for free and read, get some more information on the IJVM in that chapter. So next part, Atse will talk about the C programming language. So have fun.